Yesterday we talked about the Josephson effect. Which was discovered by Josephson in 1962, and it is the phenomenon of tunneling by Cooper pairs. Quantum mechanical tunneling by Cooper pairs across a gap, across an insulating layer, which is a very narrow insulating gap, of about 10 to 20 angstroms thick, extremely narrow. So, we have a superconducting, a junction of superconductors, a pair of superconductors, with a gap between them, which can be normal or insulating. Gap. So, the Josephson tunneling demonstrates the quantum mechanical nature of the superconducting state, and this tunneling is described by considering the two superconductors as two quantum systems and writing the Schrodinger equation. Where phi 1 and phi 2 are the quantum mechanical wave functions, and a similar equation for the second superconductor and the time dependence of its wave function, which is given by so these are the basic equations, and if we have identical superconductors, for simplicity, then the H1 phi 1 equal to H2 phi 2 equal to E0 phi 1 or phi 2. So, that is a common energy, so which can be ignored, and if this junction is biased by a voltage U, then the equations get modified to taking the 0 of energy in the midway of the gap, and a similar equation for phi 2 dot. Where phi 1 and phi 2 are of the form now these phi 1 and phi 2 are the quantum mechanical phases, and N1 and N2 are the densities of the Cooper pairs in the two superconductors. So, such that, so with this we get, this gets modified to and a similar equation and then we just multiply this equations by cos phi 1 and this by sin phi 1 and then subtract, then we get the final equations for the time dependence of the charge densities. And similar equations for the time variation of the phis, the phases. Plus minus Qu by 2h cross here plus Qu by 2h cross. So, for identical superconductors we can take N1 to be equal to N2 and so on, so that we get finally for identical superconductors we get the particularly simple equations of the form and so these are the governing equations for the Josephson effect, which tell you that even in the absence of a voltage you have a Josephson current given by the time variation of the charges. So, this represents the flow of Cooper pairs across the gap, and the Josephson current is determined by the phase difference, the quantum mechanical phase difference and the tunneling Hamiltonian T, the coupling between the two superconductors, and the phase itself in the presence of an applied voltage biasing the junction, the phase changes at a rate given by Qu by h cross. So, those are the principal results of the Josephson effect. So, this means that the quantum mechanical phase difference phi 2 minus phi 1 between the two superconductors is just 1 by h cross into Q is twice the electronic charge because of pairing, as we know, times u times t plus any initial phase difference which might already be present. So, the Josephson current which goes as n 1 dot is 1 by h cross 2 t n sin omega j t plus delta phi 0, where omega j is the Josephson frequency. which is given by 2 EU by H cross, and this is the Josephson current. So, this means that as I said, even in the absence of a voltage across the tunnel superconducting tunnel junction, there is a current which is known as usually known as the DC Josephson effect, and in the presence of a biasing voltage U, there is an AC Josephson effect which tells that this quantum mechanical phase changes with in proportion to the applied biasing voltage, and correspondingly the AC Josephson effect gives you the Josephson current, which changes, which is a sinusoidal function of the Josephson frequency, which in turn depends is equal to 2 EU by H cross. So, this is given schematically by the IV characteristic. So, that gives this is the 0 bias, and that is the Josephson current, and then this settles down to a constant value till it shoots up again and goes up like this. So, this is single particle tunneling. When the Cooper pairs are broken, at sufficiently large biasing voltages equal to the gap voltage, the Cooper pairs are broken, and this corresponds to the tunneling current due to the single particle tunneling, whereas this is the Josephson or pair tunneling. And if we have, in addition to a DC bias, if we have U, if it is U naught plus a small modulation, a sinusoidal voltage superposed on the biasing voltage, substituting here, we find that the Josephson current shows a frequency modulation. So, which corresponds to some and different frequencies corresponding to the well known side bands in a frequency modulated current. So, this is the basic functioning mechanism of the functioning of the Josephson junction, and as I mentioned yesterday, the importance of the Josephson junction consists in the fact that you can use two Josephson tunnel junctions. Which are identical, and then you have, let us call them A and B. Then following the original treatment, we can write I A is some I 0 sin delta A, whereas I B is I 0 sin delta B, where delta B minus delta A is 2E by H cross integral A dot dl, because as we explained earlier, the quantum mechanical phases will depend on the line integral of the vector potential or by Stokes theorem, and this is nothing but the magnetic flux. So, this means that I can write delta A and delta B as some delta naught minus E by H cross integral B dot ds, and delta B as some delta naught plus E by H cross. Therefore, the current which depends on the phase difference, the Josephson current across such a device where there is the current flowing through this pair of Josephson junctions becomes I equals I naught sine delta naught plus E by H cross integral B dot ds plus sine delta naught minus E by H cross integral B dot ds. And therefore, that has the form 2 I naught sine delta naught cos E by H cross integral B dot ds. So, this current across the pair of Josephson junctions will be a maximum when E by H cross or integral B dot ds equals n times pi H cross by E, and that is n times H by 2E or n phi naught. So, there will be a maximum in the Josephson current flowing across this pair of superconducting junctions. This maximum will occur whenever there is a flux quantum which is enclosed in the superconducting ring consisting of two identical superconducting tunnel junctions. So, this is the basis. So, by controlling this magnetic flux, you can control the phase factor and you will get maxima in currents like this in the Josephson current. Whenever there is a flux quantum, you get a maximum in the Josephson current, and by measuring these maxima, the flux corresponding to these maxima, one can measure the flux quantum very sensitively. So, that completes our discussion of the Josephson effect, which is a very important application of superconductors in superconducting electronic devices. Now, we pass on to a very important development which took place in the late 1980s. As we already saw, the phenomenon of superconductivity was discovered in 1911. Then the Meissner effect, which is an important aspect of superconductivity, was discovered in 1933. Then the BCS theory, the microscopic theory, as well as the Ginzburg-Landau theory were in the 1950s. But the BCS theory, while it explained everything about superconductivity, the equation for the transition temperature Tc led people to think that it is unlikely that one can discover superconductors with Tc's in excess of 30 Kelvin. Now, this is a serious drawback, because all applications of superconductors, if this is true, will take place only if the superconductor is cooled below, say, something like 30 Kelvin, and this refrigeration cost offsets most of the advantages of superconductors in devices. So, there was an imperative need for discovering some way in which a superconductor can become superconducting at a relatively high transition temperature, high Tc superconductors. There was always a quest for high Tc superconductors. They are also written in short as HTSCs. Now, there was a impasse for quite some time till in 1987. Two persons, Bednarz and Mueller, discovered a relatively high transition temperature of about 30 Kelvin in an oxide of lanthanum, calcium, barium, copper oxide. Now, this was in 1987, and then, but this was in an oxide, not in a metal. So, this is itself was a surprise, and they got the Nobel Prize in 1987 for this discovery. So, now in the very next year, Chu and co-workers made a very startling discovery. Chu et al. Discovered superconductivity in a compound consisting of yttrium, barium, copper and oxide. Now, the actual formula goes like YBA2 Cu3 O7 minus delta. So, this is 1, this is 2, this is 3, the stoichiometry, therefore, it is known as a 1, 2, 3 superconductor. And the oxygen has a stoichiometry not 7, but slightly less than 7 by a certain factor known as the oxygen deficiency delta, and that was crucial for the onset of superconductivity. The Tc in this case was greater than 90 Kelvin. So, that was a big step, big jump in the discovery of high temperature superconductors. Now, since the boiling point of liquid nitrogen is 77 K, has a boiling point of 77 Kelvin. So, one can use liquid nitrogen instead of the more expensive and more difficult to liquefy liquid helium, which boils at 4.2 Kelvin. So, this problem can be averted, and one can use the much more readily available and cheaper liquid nitrogen as a coolant for superconducting devices based on such 1, 2, 3 superconductors. Now, this was very soon followed by discovery of superconductivity in bismuth and thallium compounds. This was in 1988, and the stoichiometry was bismuth, calcium, copper oxide. So, this was known as 2223 or 2212. That gives the stoichiometry of these ternary elements in the compound. Similarly, thallium based. So, these were discovered and they had much higher superconducting transition temperatures. Now, this can be seen, table shows high Tc superconductors, the newly discovered representative compounds and their critical temperatures in degree Kelvin. So, you can see that the lanthanum barium copper oxide has a critical temperature of 36 Kelvin, while yttrium barium copper oxide has 90 Kelvin and thallium barium calcium copper oxide has a temperature transition temperature of 125 Kelvin. The mercury barium calcium copper oxide has even a higher temperature of 133 Kelvin. So, a number of materials which were more or less ceramics were discovered in quick succession, which pushed up the transition temperature to something like 133 Kelvin. But as we already mentioned, superconductors for use in practical applications need to have not only high transition temperature, but also a high critical magnetic field and a high critical current density. Now, the newly discovered superconductors also satisfy this criterion of having a high enough upper critical magnetic field. They must also have favorable mechanical properties in order to be drawn into the form of wires to be wound in magnets and so on. They must be ductile. Many of the high Tc superconductors have the disadvantage that they are brittle, and so it is rather difficult to get them in the form of wires. Flux quantization experiments carried out in these superconductors showed evidence for pairing. The measurement of the flux quantum tells you whether their pairing occurs or not. So, the mechanism of superconductivity in this is again based on some form of pairing, which takes place not between the electrons, but between holes in these superconductors. We will discuss what is a hole in the next few lectures when we come to discuss semiconductors. So, because of this, the whole nature of the superconductivity, hole pairing, they are known as p type superconductors, and this is also confirmed by the sign of the Hall constant. We will discuss these things when we discuss semiconductors. The energy gap in these cases is in the range 20 to 30 milli electron volts, and in order to understand the mechanism of pairing, whether it is the BCS type, it is necessary to find the ratio delta 0 by kBTC, the energy gap at 0 Kelvin divided by K Boltzmann constant times the transition temperature. This is in the range of 3 to 4 as against the BCS value of 1.764. Now, the dependence, there is a critical dependence, Tc depends on the oxygen deficiency parameter delta very critically. These are some of the factors which has to be understood in order to understand the mechanism of superconductivity in these compounds. The crystal structure, for example, in these compounds, most of these oxide superconductors, these are all oxides. Not metallic superconductors, they crystallize in a modified perovskite structure. For example, the oxides of the type AbO3, for example, barium titanate, a typical member of these oxides is barium titanate, which is well known as a ferroelectric material. They crystallize in the perovskite structure. The unit cell of a compound belonging to the perovskite structure is shown in the figure. This is modified perovskite structure for the barium titanate. So, the barium atoms are the big spheres, A atoms, and the copper is the B atoms, and the oxygens are at the middle of the edges. So, the barium atom sits at the body center, and the oxygens sit at the middle midpoints of the cube edges, and the copper atoms sit at the vertices of this cubic unit cell. So, that is the basic structure. So, you have a cube in which the large metal atom A lies at the body center. The smaller metal atoms B occupy the corners and the oxygen atoms are at the center of the cube edges. There is one molecule in the unit cell. The smaller metal atom B metal atom is surrounded by 6 oxygen atoms. Okay, 6 oxygen atoms forming an octahedron in an octahedral coordination. So, you have the lattice which can be viewed as being made up of a large number of such octahedral units, with each unit joined at the 6 corners with other such units at the 6 corners of the octahedron, and the interstitial positions between the octahedra are occupied by the bigger metal atom A. So, that is the basic cubic structure. Now, the yttrium barium copper oxide is a modified version of this. Now, this is shown in the next figure. Now, you have a modified version in which we are showing the unit cell is bigger with 3 perovskite unit cell cubes arranged along the C axis. You can see it is a tetragonal crystal, not a cubic one, and you have a C axis like this, and the 3 cubic unit cells are stacked along the C axis with the barium and yttrium atoms alternately occupying the body centers of the cube. The copper atoms are at the cube corners and some of the oxygen sides are not occupied. So, it is a kind of quasi tetragonal perovskite structure, which is a layered structure with alternating copper oxygen ion layers and barium or yttrium oxygen ion layers. The copper oxygen ion layers form conducting layers. So, you have a kind of quasi 2-dimensional charge transport. These copper atoms are responsible for the superconductivity. The barium or yttrium oxygen layers form insulating layers between these conducting planes. The charge carriers in the conducting layers form Cooper pairs, which move freely without getting scattered. Due to the layered structure, the oxide superconductors are strongly anisotropic. So, that is the basic crystal structure. So, you have also, in addition to these are p type because of hole pairs. One can also have n type superconductors, which are due to the formation of electron pairs. They were also discovered soon, and such as materials such as neodymium copper oxide or neodymium cerium copper oxide. So, these are n type superconductors. In addition, we also have the interesting new family of superconducting compounds based on fullerenes. The fullerenes consist of 60 carbon atoms formed in the form of a ball of diameter 7.1 angstroms. Now, this is known as C60, and if you take a crystalline film of carbon, fullerene carbon, and evaporate potassium atoms in, so you have a potassium vapor, then you have the formation of K3C60, where the potassium form go into this ball. So, then this becomes a metallic material with a superconducting transition of 19.3 kilo. So, these are the more recent developments in the area of high Tc superconductors. The elucidation of the mechanism of superconductivity in these materials remains to be discovered. Similarly, there are a lot of interesting developments in regard to the technological exploitation of these newly discovered high temperature superconductors. Well, this whole field is in a state of flux, so we leave it at this stage.